Hello! The topic of today's lesson is statics. In the previous video we studied dynamics, which explains why objects move. Now we'll focus on why objects stay at rest by looking at applied forces and torques in equilibrium. First, we'll briefly go over the key principles of statics, Newton's first law and principle of torques. Then we'll apply these ideas in practice. We'll analyze different cases, including balancing board, supported beam, leaning plank and tipping box, all using the same fundamental rules. Let's get started. Statics is a branch of mechanics that deals with the equilibrium of bodies under the action of applied forces and the resultant torques. In some textbooks, torque is also referred to as moment. Statics is based on two fundamental principles. The first principle is Newton's first law. A body remains at rest if the sum of all forces acting on it is zero. The second principle is the principle of torques. A body remains at rest if the sum of the torques of all applied forces is zero. The torque of a force is a vector quantity, but in school-level statics we only consider its magnitude. For our purposes, it's enough to know that torque is found by multiplying the force by its level arm. The level arm is the shortest perpendicular distance from the pivot point to the force's line of action. Another key aspect is the sign convention for torques. A force that tends to rotate the object clockwise about the pivot is considered positive. A force that tends to rotate the object counterclockwise about the pivot is considered negative. If this explanation seems unclear right now, don't worry, we will go through visual examples to make everything more intuitive. Let's get started. A uniform board of length 1.5 meter and mass 1 kilogram is balanced on a fulcrum at its center, forming a lever. Two weights are placed on the board. The first weight, with a mass of 1 kilogram, is positioned 0.6 meters from the center. The second weight has a mass of 2 kilograms and is placed at an unknown distance from the center. We need to determine how far from the center the second weight must be placed for the system to remain in equilibrium. This is a simple example of a lever balance, which follows the law of the lever. Now let's analyze the forces acting on the board. Since we are considering equilibrium, we need to focus only on the forces that act on the board itself. These forces include the gravitational force on the board, the normal force of the fulcrum, and the weights of the two objects pressing down on the board. So there are 4 forces in total. It's important to note that all these forces lie in a single plane. In real-life applications, especially in university-level physics, you might encounter three-dimensional problems. However, in high school physics, we typically simplify problems to a two-dimensional plane. I will refer to it as the plane of the page. Now let's analyze the conditions for equilibrium. Since the board is at rest, the sum of all forces acting on it must be zero. In vector form, this can be written as all forces act along the vertical direction, so we only need to consider a single coordinate axis. Let's define the y-axis as pointing upward and project all forces onto this axis. From this, we can determine that the normal force of the fulcrum must be equal to the sum of the 3 downward forces. Now let's consider the second condition for equilibrium, the balance of torques. Torque is calculated as the product of force and the perpendicular distance from the fulcrum. Since all forces lie in the plane of the page, the most convenient choice for the pivot point is the fulcrum itself. The axis of rotation is perpendicular to the plane of the page and passes through the fulcrum. To maintain equilibrium, the sum of all torques acting on the board must be zero. Now let's analyze the torques created by the two weights. For the first weight, the distance from the fulcrum is L1, 0.6 meters. The force is equal to m1 multiplied by acceleration due to gravity. Since the force tends to rotate the board counterclockwise, its torque is negative. For the second weight, the distance from the fulcrum is L2, which we need to determine. The force is equal to m2 multiplied by gravity. Since the force tends to rotate the board clockwise, the torque is positive. Setting the sum of torques to 0 and solving for L2, we get. Thus, the second weight must be placed 0.3 meters from the center of the board. Now let's check if the choice of the pivot point affects the result. We can select an arbitrary point O at the pivot and recalculate the torques. In this case, we determine the perpendicular distances of each force from this new pivot. Let's define the lever arm of force F1 as A. This force tends to rotate the system clockwise about the chosen pivot point. The torque of F1 is positive and equal to the force multiplied by its lever arm. The lever arms of the normal force and the gravitational force are the same in this case, so we will denote them as B. The gravitational force tends to rotate the system clockwise, while the normal force tends to rotate it counterclockwise. Therefore, the torque of gravity is positive and the torque of the normal force is negative. Now let's define the lever arm of force F2 as C. This force tends to rotate the system clockwise, so its torque is positive as well. Since the object remains in equilibrium, the sum of all torques must be zero. We can express the lever arm of gravitational force and the normal force as the sum of A and L1. The lever arm of F2 is the sum of A, L1 and L2. From Newton's first law we know that normal force is equal to the sum of forces F1, F2 and mg. Substituting this into the torque equation, simplifying and combining like terms, we arrive at the same result as before. This confirms that the choice of pivot doesn't affect the final answer. I encourage you to practice this method by selecting a different pivot, such as the location of the first or second weight, and solving for the distances yourself. This is a valuable skill for understanding statics problems more deeply. Finally, let's briefly discuss the stability of the system. This equilibrium is unstable, which means that if the board is slightly disturbed, it will not return to its original balanced position, but will tilt further. This is an important factor to consider in real-world applications of levers and balance. Now let's move on to the next example. A board with a mass of 5 kg and a length of 2 meters is resting on two supports. The distance from the left edge of the board to the left support is 0.5 meters. The distance from the right edge of the board to the right support is 0.75 meters. We need to determine the force exerted by the board on each of the supports. Now let's analyze the forces acting on the board. This includes the gravitational force, which is equal to the weight of the board acting downward at its center, and the normal forces exerted by two supports, which are directed upward. Let's denote these forces N1 and N2. Now let's consider the conditions for equilibrium. Since the board is at rest, the sum of all forces acting on it must be zero. We can express this by projecting the forces onto the vertical axis. This gives us the first equilibrium condition. The second equilibrium condition is based on the principle of torques. Since the left support is our pivot, the lever arm of force N1 is zero, meaning that the torque of this force is also zero. The lever arm of the gravitational force, which acts at the center of the board, can be denoted as L1. This force tends to rotate the board clockwise, so its torque is positive and equal to the weight of the board multiplied by L1. The lever arm of the reaction force of the right support, which we denote as L2, causes counterclockwise rotation. Therefore, its torque is negative and equal to N2 multiplied by L2. Now let's express L1 and L2 in terms of known values L, A and B. This gives us a system of two equations with two unknowns. Solving for N1 and N2 will give us the forces exerted by the board on each support. I suggest calculating these values independently. Now let's think about what happens if we press down on the left edge of the board. Clearly, in this case, the force exerted by the board on the left support will increase, while the force on the right support will decrease. You can try to determine how these forces change on your own. For this lesson, let's explore the condition under which the board will lift off from the right support. If the board lifts off from the right support, it means that the board will stop exerting any force on the right support. As a result, the support will also stop exerting a force on the board. Thus, the condition for the board lifting off the support is that the normal force at that support becomes zero. This is an important concept often used in physics problems. Now let's apply the principle of torques in this case. The lever arm of force F relative to the chosen pivot point is equal to A. Since the force causes counterclockwise rotation, its torque is negative. With this, the torque equation takes the following form. From here we can solve for the force F. You can calculate its value independently. If we continue increasing force F, the board will begin to move. Now let's move on to the next example. A board is leaning against a smooth wall. The mass of the board is 2 kilograms. Its length is 1.5 meters and the angle between the board and the floor is 60 degrees. We need to determine the friction force between the board and the floor, as well as a normal force from the wall. The board is acted upon by 4 forces. For the board to remain at rest, the sum of all applied forces must be zero. Now let's introduce a coordinate system. We will direct the x-axis horizontally and the y-axis vertically. Next, we will project the force equilibrium equation onto this axis. The second condition for equilibrium is the principle of torques. The most convenient pivot point for calculating the friction force is the point where the board touches the wall. Up to this point we have considered equilibrium for cases where all applied forces were parallel. In this problem that's not the case. A quick reminder. The lever arm is the shortest perpendicular distance from the pivot to the force's line of action. It's not simply the distance from the pivot to where the force is applied. All forces in this problem lie in the same plane. To find the distance from the pivot to a force, we need to draw a perpendicular from the pivot to the force's line of action. We will denote the distance from the pivot to the normal force from the floor as L1. To find this distance, we can analyze a right triangle. The segment L1 corresponds to the adjacent leg of the triangle relative to the angle alpha, so L1 can be found at the product of the hypotenuse and cosine of alpha. The segment L2 corresponds to the opposite leg of the triangle, so it can be found at the product of the hypotenuse and the sine of alpha. Now let's analyze the torques. The normal force from the floor rotates the board clockwise. Its lever arm is L1, so its torque is determined by this expression. The friction force rotates the board counterclockwise. Its lever arm is L2, so its torque is. The gravitational force also rotates the board counterclockwise. Since gravity acts at the center of mass, which is midpoint of the board, its lever arm is half of L1, so its torque is. Since the board remains in equilibrium, the sum of these torques must be zero. From these equations, we can see that the normal force from the wall is equal in magnitude to the friction force from the floor. Additionally, the normal force from the floor is equal in magnitude to the gravitational force. Now let's express the friction force in terms of the gravitational force. At this moment the board remains at rest. However, if we start decreasing the angle between the board and the floor, at some point the board will begin to slide. If the board starts to slide, it means that the friction force has reached its maximum possible value, which is equal to the coefficient of friction multiplied by the normal force. If this concept is unclear, I recommend reviewing my video on dynamics. From this we can determine the coefficient of friction between the board and the floor. Now let's move on to the final example. A box with a mass of 10 kilograms, a height of 1.4 meters and a width of 0.7 meters is standing on the floor. The coefficient of friction between the box and the floor is 0.5. What force must be applied to the top edge of the box to make it tilt? And what force is needed for it to fall over completely? While the box is simply standing still, only two forces act on it. These two forces are equal in magnitude and opposite in direction. Since the mass of the box is 10 kilograms, both the gravitational force and the normal force are equal to approximately 100 newtons. When we start applying a horizontal force to the top edge of the box, a friction force between the box and the floor appears. The maximum possible friction force is given by the formula. Substituting the given values, the maximum possible friction force is 50 newtons. It's important to note that along the vertical axis, the only forces acting on the box are gravity and the normal force. This means that the normal force will always be equal to the gravitational force. Along the horizontal axis, only two forces present: the force with which we push the box, the friction force opposite the motion. As long as the applied force doesn't exceed the maximum possible friction force of 50 newtons, friction will simply adjust to match the applied force. The box will only start sliding when the applied force exceeds 50 newtons, assuming it doesn't tip over first. To determine the force needed to tilt the box, we use the principle of torques. As we apply a horizontal force, the magnitude and direction of the normal force do not change, but its point of application shifts. When the box begins to tilt, it means that the normal force acting only on the right edge of the box. Let's apply the principle of torques for this case. It's most convenient to take the pivot point at the bottom right corner of the box. The lever arm of the applied force is equal to the height of the box. The lever arm of the gravitational force is half the width of the box. The lever arms of the friction force and the normal force are zero in this case, because they act through the pivot point. Since the applied force rotates the box clockwise and the gravitational force rotates counterclockwise, the torque equation is set up as follows. Solving for the force F, we find that the minimum force required to tilt the box is 25 newtons. If we continue applying a force greater than 25 newtons, the box will tilt further. However, for the box to completely fall over, the torque of the gravitational force must change its direction. This happens when the center of mass of the box is directly above the pivot point. At this moment, even if we stop pushing the box, it will fall over its own. That's all for today. Thank you for watching. If you have any questions, feel free to leave them in the comments. I'll try to answer them. Don't forget to subscribe the channel and leave a like. See you in the next video.